hopefully you've already gone through these, at least attempted them, and you're just coming to this video needing a bit of just help because you've kind of like, okay, exactly how do I do this? If you haven't even started or even tried to do these, then stop this video now, go give them, a run through, and then come back to the video if you get stuck. Otherwise, there's just no benefit in this, and it's really not going to help you. You're just kind of wasting your time. So I'm going to assume I'm talking to you guys who have attempted this video, or these sheets. Number one, I gave you a hint there. That is just a dilution, which is, M1V1 equals N2V2. And so you should have found the whole solution is a 6 molar solution. On number two, you're going to take that exact solution and you're diluting it more, and then you have to find the pH. Now remember, the pH, you always find the pH is going to be, pH equals the negative log of the hydrogen ion concentration. So you need to find hydrogen ion concentration. So your first thing is, this is a weak acid. So the first thing I like to do to work through these is to go ahead. Well, first of all, you need to do the dilution for one. And so the molarity of the new solution was 0.2 molar. Okay, so that's your solution. Now, and then the next step you're going to want to do is write yourself a weak acid equation. It's going to disassociate, of course, reversible arrow because it doesn't completely become product. Some of it stays as a reactant. That's exactly what you're trying to find. And it tells you that the pH, using the pH here, you can go backwards to find the hydrogen ion concentration. And so that's how I found the hydrogen ion concentration. So in the case using your calculator, you're going to want to go 10 to the negative pH to get, and so that's how I found the hydrogen ion concentration. So then once I found the hydrogen ion concentration, then I could go ahead and find exactly how much hydrogen ion concentration was formed, how much acetate was formed, and then how much residual acetic acid was left over. And then doing all that, plug it all into your acid dissociation constant expression and solve. And we got 1.6 times 10 to the negative 5, which is small. So this has a very low dissociation. And then you're going to take this answer and you're going to use it multiple times through this. Okay, next one. It says, okay, now this time we're going to put in sodium acetate, which is a salt, this is, if you look at it, this is going to be a weak base. It's going to be a conjugate base of the weak acid that went in. So in this case, you're finding a buffer. And so in order to find your pH of your buffer, you're going to go through you're going to find out, one, how much of the sodium acetate went in, and that's what I did here, just the number of moles. And then I needed to find what the concentration of that is, so I turned moles into concentration by dividing by the volume. And again, start all over. Here's my weak acid equation, except at this time we're not just starting off just with acetic acid. We end up with some of the conjugate base in here as well, which is 0.201. And so with 0.201, then we can do our change, we can find out equilibrium, and we're going to end up, we're trying to find X. This is what we're trying to find, because that's hydrogen ion concentration, and then we can find pH from there. So I'm going to go ahead, and because it's very small, I'm going to assume we're going to take away those X's, because they're not going to matter for the final answer due with our significant figures. And so then I even simplified it. If you get to this step right here, you can tell it wasn't even going to, I just kind of said that 0.2 and 0.201 were the same thing. So those cancel out, and you get X equals 1.6 times 10 to the negative, and then you 1.6 times 10 to the negative fifth, and so that's all you have to do is the negative log to get the pH of the buffered solution. pH of the buffered solution. On this next one, okay, these are two different problems. So they're really similar. And once you solve for one, the other one's really easy. this is what happens if when you put in both an acid and a base into your buffer. So again, using the same from last time, and you're splitting it into two different samples, like a 400 milliliter. Okay, first thing you do, you need to find your initial amounts of everything. And so using moles equals molarity times liters, you end up getting moles of acid, end up getting the moles of HA, which is the acetic acid. I'm just abbreviating to HA, so I didn't have to say for room. And then you have to find your moles of acetate ion. And all this came from the problem before. Okay. So now, what's the next thing that happens? Okay, well, this acid that you're dropping in here, HA, it's going to react with the conjugate base of the buffer, and you're going to form that weak acid back, HA. And how much of it did it eat up? Well, did it eat up all the acid? Yeah, and you're left over with some of the conjugate base, 0.05 moles, and you're going to form 0.11 moles of HA, because whatever was used up on the reactant side created more product. Okay, so now you get your concentration of your base and your acid by taking the number. These were all number of moles here that I found, and then I just went ahead and got a concentration by dividing it by the number of liters, which was 405 milliliters, because remember you have 5 milliliters coming from the acid, and then you had 400, so add those together and you get your two concentrations, and then I just plugged them into HH, which is the pH of the pKa plus the log of the base over acid, and I get 4.45. This problem is almost the exact same. For the base, it's just this is different. The reaction that occurs is different, because this time your base, your hydroxide, is going to react with the weak acid to form the conjugate base. But other than that, it's the exact same, so I don't have quite as much work shown there. All right, number 5 is just calculating pH, and so that's that. So there's not very much acid in that one, so the pH is 5. And then this one so then number 6 goes through and says, okay, what's going to happen to this if you drop in not concentrated, but 6 molar acid? Not very much, 0.05 mils. And so it goes through. You need to, your steps on this one is you need to find your moles of acid contributed from this part, and then you have to calculate your number of moles from this part, which is again just moles equals molarity times liters or volume to get moles. And then you're just going to add these two together to get your total number of moles, and then to get your concentration, divide by the total number of liters. Now you have your molarity, and now you can find the pH. So you can see that when you drop in your HCl into a buffered solution, like up here, the pH barely moves. If you drop in an HCl into an unbuffered solution, it changes quite a bit. Okay, I gotta fly through this last page, otherwise YouTube's not gonna let me put it on there. Number 7 is the exact same type of problem. The only difference here is it's a base, and so remember your acid and your base are going to actually cancel each other out. They're going to react together to make water, and so instead of adding your moles of acid, your moles of base to moles of acid, you actually subtract. And you get your moles of hydroxide. Then once you have your moles of hydroxide, you go ahead and take the find the concentration, then find the pOH, and then you can find the pH from there, because remember, the pH plus the pOH equals 14. All right, very last one here. Okay, these are just some mixtures, and you're trying to predict what's actually the product is going to be. First one is a strong base and a weak acid go together, and you end up getting a weak base and water. In HCl, you have a strong acid, and then this is a neutral salt. And the reason it's a neutral salt because the two parents are of the strong base and a strong acid. And so since this neutral salt is not really doing anything in the reaction, you just end up getting a strong acid at the end. And this very last one, you have a strong acid and a weak base, and the result is a weak acid. So I hope this helps.